Welcome to the session on uniform distribution. Uniform distribution is a special type of continuous probability distribution. The definition is a continuous random variable capital X is said to follow a uniform distribution if its probability density function f of x is given by f of x is equal to 1 by beta minus alpha, where alpha less than or equal to x less than or equal to beta, and f of x is equal to 0 otherwise. This is the PDF, that is probability density function of the capital X, where x follows uniform distribution. Here alpha and beta are two constants. They are called the parameters. Alpha and beta are the parameters of the distribution. We can verify that this f of x is a PDF. The two conditions for a function f of x to be a PDF of a continuous random variable x is, first one is f of x is greater than or equal to 0 for every values of x, and the second condition is integral from minus infinity to infinity f of x dx is equal to 1. These are the two conditions for a function f of x to be a PDF. We can verify these two. Here note that f of x is 1 divided by beta minus alpha, where alpha and beta are two constants. Here beta is greater than alpha, therefore this term 1 by beta minus alpha is always greater than always non-negative, and f of x is equal to 0 otherwise. Therefore obviously this function is greater than or equal to 0 for every x. The first condition hold, and now we can verify the second condition. Here integral from minus infinity to infinity f of x dx is equal to integral from minus infinity to a f of x dx plus integral from here minus infinity to alpha f of x dx plus alpha to beta f of x dx plus integral from beta to infinity f of x dx, which is equal to integral from minus infinity to alpha. Here the function is 0 because the function f of x is equal to 1 by beta minus alpha is defined for x in between alpha and beta, and all the other cases the function is defined as 0. Therefore here the limit of integration is minus infinity to alpha, means x is less than or equal to alpha. In that case the function is defined as 0. Therefore 0 integral minus infinity to alpha 0 dx plus integral from alpha to beta. Here f of x is 1 by beta minus alpha dx plus in this case also integral from beta to infinity, means the limit of integration is x is greater than beta. In this case f of x is 0. Therefore this is equal to integral from alpha to beta. We can take 1 by beta minus alpha outside f of x dx. That is equal to 1 by beta minus alpha into x between the limits alpha and beta, that is 1 by beta minus alpha into beta minus alpha, which is equal to 1. Therefore, the second condition is also satisfied. Hence, this function can define the PDF. Now, we have to find the arithmetic mean of x. Consider a random variable capital X having the uniform distribution with parameters alpha and beta. X follows uniform distribution with the parameters alpha and beta. Then f of x is 1 by beta minus alpha for alpha less than or equal to x less than or equal to beta, and f of x equal to 0 otherwise. Therefore, the arithmetic mean, simply the mean of x is the expectation of x. By the definition of expectation, it is integral from minus infinity to infinity x into f of x dx. That is equal to integral from minus infinity to alpha x into f of x dx plus integral from alpha to beta f of x dx, x into f of x dx plus integral from beta to infinity x into f of x dx. Which is equal to, in this case, function is defined as 0, and also in this case it is 0. Therefore, we have to evaluate the middle integral only, which is equal to integral from alpha to beta x into, here f of x is 1 divided by beta minus alpha dx is equal to, here 1 by beta minus alpha is a constant which can be taken outside of the integral. Therefore, this is equal to 1 by beta minus alpha into integral from alpha to beta x dx. That is 1 by beta minus alpha into, here integral x dx is x square divided by 2 between the limits alpha and beta, which is equal to 1 by beta minus alpha into 1 by 2 into beta square minus alpha square. That is equal to 1 by beta minus alpha into 1 by 2 into this beta square minus alpha square can be written as beta plus alpha into beta minus alpha. This beta minus alpha and beta minus alpha cancelled. Therefore, mean of x is equal to beta plus alpha divided by 2 or alpha plus beta divided by 2. That is, the arithmetic mean for a uniform distribution is the average of the two parameters alpha and beta. Now, we have to find the variance of uniform distribution. Consider a random variable capital X having the uniform distribution with parameters alpha and beta, and the corresponding PDF is f of x equal to this. Now, by the definition of variance, in terms of expectation, we can write the definition of variance of x as expectation of x square minus expectation of x the whole square. Here, expectation of x is the arithmetic mean, which is equal to average of the two parameters alpha and beta. Therefore, we have to find E of x square only. By the definition of expectation, E of x square is equal to integral from minus infinity to infinity x square into f of x dx, which is equal to, we can split this limit of integration minus infinity to plus infinity into three parts. That is, one is from minus infinity to alpha and alpha to beta, then beta to infinity. In the first and third case, the function is defined as 0. Therefore, we have to evaluate the middle integral only, that is integral from alpha to beta x square into f of x dx. In this case, f of x is defined as 1 divided by beta minus alpha dx, which is equal to 1 by beta minus alpha is a constant that can be taken outside of the integral. Therefore, E of x square is equal to 1 by beta minus alpha into integral alpha to beta x square dx. That is equal to 1 by beta minus alpha into integral x square dx is x cube divided by 3 between the limits alpha and beta. That is equal to 1 by beta minus alpha into 1 by 3 into here beta cube minus alpha cube. Which is equal to 1 by 3 into beta minus alpha into this beta cube minus alpha cube can be written as beta minus alpha into beta square plus alpha beta plus alpha square. Therefore, this beta minus alpha and beta minus alpha cancelled, and E of x square is equal to beta square plus alpha beta plus alpha square divided by 3. This is the expectation of x square. And so, variance of x is v of x is equal to E of x square minus E of x the whole square. We substitute this value of E of x square here. We get beta square plus alpha beta plus alpha square divided by 3 minus E of x is alpha plus beta divided by 2. Therefore, E of x the whole square means alpha plus beta square divided by 2 square is 4. This is equal to beta square plus alpha beta plus alpha square divided by 3 minus here alpha square plus 2 alpha beta plus beta square divided by 4, which is equal to 4 beta square plus 4 alpha beta plus 4 alpha square minus 3 alpha square minus 3 into 2 alpha beta is minus 6 alpha beta minus 3 beta square all divided by 3 into 4 is 12, which is equal to 4 beta square minus 3 beta square is 1 beta square, 4 alpha square minus 3 alpha square is 1 alpha square, and 4 alpha beta minus 6 alpha into beta is 4 minus 6 is minus 2 into alpha beta all divided by 12, which is equal to, this is beta minus alpha the whole square divided by 12. That is the variance of x is beta minus alpha the whole square divided by 12. Now we have to find the moment generating function of uniform distribution. Note that here variance of x is beta minus alpha the whole square divided by 12 means this implies that standard deviation of x is positive root of the variance of x, that is positive root of beta minus alpha whole square divided by 12, which is equal to beta minus alpha divided by square root of 12. Now we have to find out the moment generating function. By the definition, moment generating function is mxt is equal to, in terms of expectation, it is expectation of e raised to tx, which is equal to, by the definition of expectation, e of e raised to tx is integral from minus infinity to infinity e raised to tx into f of x dx. Here the total limit of integration is minus infinity to plus infinity. Here the function is defined as like this. Therefore, we can split this limit of integration into 3, in which the first one, that is the integral from minus infinity to alpha e raised to tx f of x dx is 0, and the middle term, that is integral from alpha to beta e raised to tx into f of x is, in this case, 1 by beta minus alpha dx, plus in the third case the limit is beta to infinity, in which case the function is defined as 0. Therefore, mxt is equal to integral from alpha to beta e raised to tx into 1 by beta minus alpha dx, that is 1 by beta minus alpha into integral alpha to beta e raised to tx dx. On integration, we get this is equal to 1 by beta minus alpha into, here integration with respect to x, therefore it is e raised to tx divided by coefficient of x is t between the limits alpha and beta, which is equal to 1 by beta minus alpha into t, that is 1 by t into beta minus alpha e raised to beta t minus e raised to alpha t, that is e raised to beta t minus e raised to alpha t all divided by beta minus alpha, which is the t into beta minus alpha in the denominator, which is the moment generating function of the uniform distribution. Now we have to find the cumulative distribution function of uniform distribution. Consider a random variable capital X having uniform distribution with parameters alpha and beta, then the probability density function is this. Now, by the definition of cumulative distribution function, it is denoted as capital F, which is equal to probability of x is less than or equal to some particular value of x, which is equal to integral from minus infinity to x f of x dx. Here the function is defined as a continuous function. Therefore, capital F of x is, that is the distribution function, is integral from minus infinity to x f of x dx. We consider the case x less than or equal to alpha. First case is x less than or equal to alpha. In this case, the function is defined as 0. Therefore, capital F of x, that is the cumulative distribution function in this case, is 0, because the PDF is 0 in this case. Now, we consider the second case as alpha less than or equal to x less than or equal to beta. X lying between alpha and beta, including alpha and beta. In this case, the function is defined as 1 by beta minus alpha. Therefore, here by the definition of cumulative distribution function, f of x is equal to integral from minus infinity to x f of x dx. We can write this integral as integral from minus infinity to alpha f of x dx plus alpha to x f of x dx. This is the definition. The limit is from minus infinity to x. In this case, we can split this limit of integration into two, that is one is from minus infinity to alpha and then alpha to x, which is equal to, here x is less than or equal to alpha, in which case the function is defined as 0. Therefore, this term will become 0 plus integral from alpha to x. Here f of x is defined as 1 by beta minus alpha dx, that is equal to 1 by beta minus alpha is a constant, integral that is equal to 1 by beta minus alpha into integral from alpha to x dx, that is 1 by beta minus alpha into integral dx is x between the limits alpha and x, that is equal to x minus alpha divided by beta minus alpha. This is the cumulative distribution function in the second case. Now, consider the third case as x is greater than or equal to beta. In this case, the definition of cumulative distribution function is this. This limit of integration minus infinity to x can be split into 3 as integral from first is integral from minus infinity to alpha f of x dx plus integral from alpha to beta f of x dx plus integral from beta to infinity, beta to x f of x dx. That is equal to, in this case, x is less than or equal to alpha, function is defined as 0, therefore this term will become 0, plus integral from alpha to beta, here the function is defined as 1 by beta minus alpha dx plus integral from beta to x. In this case, the function is defined as 0, that is the limit of x is greater than beta, means f of x is defined as 0. Therefore, this is equal to 1 by beta minus alpha into, on integration we get x between the limits alpha and beta, that is 1 by beta minus alpha into beta minus alpha, which is equal to 1. Therefore, we can express the cumulative distribution function as f of x is equal to 0 for x less than or equal to alpha, and it is beta minus alpha, x minus alpha divided by beta minus alpha. For alpha less than or equal to x less than or equal to beta, and it is 1 for x greater than or equal to beta. This is the cumulative distribution function of the uniform distribution. Now, let me conclude this session. Thank you for watching this class. Have a nice day.